Hello, my name is Bernard Chang, and this is my ENME489Y remote sensing final project video. In this course, we learn the fundamentals of remote sensing, focusing primarily on light detection and ranging, or LiDAR. As part of this course, students were tasked with collecting 3D measurements of a specific target on the University of Maryland campus by designing, integrating, and testing their own LiDAR systems using Raspberry Pi and OpenCV-based platforms. Eventually, Dr. Mitchell would like to compile each of these 3D point clouds into an ever-evolving 3D map of campus. So what is remote sensing? The USGS defines remote sensing as the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance from the targeted area. Essentially, it is obtaining information without having a sensor in direct contact with the target. Examples of remote sensors include LiDAR and radar, in addition to sonar, seismograms, ultrasounds, and more. Remote sensing is used in a variety of fields, many of which are in the earth science disciplines. However, it also has military, commercial, planning, and humanitarian applications that can be used for anything from navigation to forecasting to surveillance. Remote sensing is split into two types, passive and active. A passive sensor is an instrument designed to receive and measure natural emissions such as photographic, thermal, infrared, and seismic sensing. Active sensors are instruments used for measuring signals transmitted by the sensor that were reflected, refracted, or scattered by the target. This brings us to LiDAR. LiDAR, or light detection and ranging, is an active remote sensing technique that uses photons in the form of a pulsed laser to measure ranges to an object. Using these light pulses and other recorded data, one can stitch together a three-dimensional surface characteristics of the scanned object. This method is commonly used in geodesy, but is used in many other applications as well, including control and navigation for autonomous vehicles. The LiDAR equation shown here is the governing equation for any LiDAR system and describes the relationship between the power returned to a receiver for a given transmitted laser power, optical properties, medium of propagation, and target properties. Here the number of photons detected, ns, is equal to the number of transmitted photons, nl, multiplied by losses due to scattering, beta, system collection, transmission, t, efficiency, eta, plus some level of noise, nb. Computer vision deals with how computers see and understand digital images and videos. From an engineering perspective, ideal computer vision would enable computers to see, identify, and process images in the same way a human does. Applications include automatic inspection, identification, detecting events, navigation, and more. In the context of this project, I built a simple LiDAR system that takes 3D measurements of the Testudo statue in front of Van Munching Hall, using a line laser and a Raspberry Pi. I took measurements at integer degrees on all four sides, resulting in about 30 measurements per side. By applying a color mask on the images, I was able to use computer vision techniques to find the number of pixels between the identified laser line and a datum axis on the screen. With simple geometry, the Python script can calculate the distance from the source to the statue. The target I chose for this project was the Testudo statue in front of Van Munching Hall, shown here on the map. I chose this target mainly because it's a new statue on campus, installed in 2018, so it is likely that no one had scanned it before. It had an interesting geometry with a rectangular base, which would help with data collection. It is in a large flat space, so there's plenty of room to put my equipment, and I did not have to worry about compensating for the angle of incline. And it is far from the street, so I wasn't too concerned about headlights of cars or buses. My LiDAR system consisted of a line laser, which acted as my transmitter, and a Raspberry Pi and 8 megapixel camera, which acted as my receiver and data acquisition system. Like many of my peers, I 3D printed the provided chassis, which held my system components together. Unfortunately, the chassis warped a little bit during the printing process, so there's a bit of curvature and misfit between the two pieces. However, by adjusting my calibration offset values, this posed no issues in data collection. Since the pieces were printed separately and did not fit together well, I was unable to epoxy them together, and so had to use duct tape. This did the job as the two pieces were relatively rigidly connected. My line laser did not fit in the hole, even though I adjusted the size in the CAD file, so I had to file out the hole and eventually just cut off the top. After adjusting the laser direction using laser alignment image.py, I made sure the line laser was held in place by using hot glue and more duct tape. My line laser is powered by an Arduino Uno, which I zip tied to the chassis, which is then powered by a power bank, which I taped to the tripod during trials. On the other side of the chassis, I have a Raspberry Pi zip tied to the chassis and Pi camera, which is screwed in using a camera mount that came with the kit. The chassis is connected to the tripod using a 3D printed tripod mount, and I duct tape my phone to the chassis during trials to take angle measurements. The LiDAR system built in this course uses geometrical and triangulation techniques to measure distance from an object. By taking an image, we can measure the perpendicular distance in number of pixels from a laser point to a central datum axis. By using simple geometry, this distance and a known separation distance between the laser and camera, and also taking into account small amounts of error, we can calculate the distance from the source to an object. Since a line laser is nothing more than an array of single laser points, we can extrapolate this method to gather an array of measurements along a line. Shown here are my calibration curves for a single beam laser and line laser. The single beam laser did not match the theoretical curve very well. This is likely due to large errors in separation distance and radian offset values, since I did not have my LiDAR system ready at this time. My line laser calibration agreed with the theoretical curve quite well after reducing my radian offset value by 2 orders of magnitude. The system is in closest agreement with the curve above 5 feet, so I made sure that when taking measurements I was 6 feet away from the statue. For data collection, I had my tripod situated 6 feet from the base of the statue. For all 4 sides of the statue, I started at the bottom of the base and varied the angle by increments of 1 degree until I reached the top of Testudo's shell. This resulted in about 30 measurements per side. By running data collection2.py and inputting angle measurements from my phone, the Python script took an image of the field and saved it using the angle measurements as the name. Due to ambient lighting, I increased the exposure of the camera to 2 seconds. I encountered several challenges when doing this project, the first of which came from the physical nature of the statue itself. The base of the statue is black, and the statue itself is dark copper. This means that the laser light did not reflect very well. In order to overcome this, I went back out into the field and covered the base with white printer paper and Testudo with baking soda in an attempt to increase the reflectivity of the surface. Further, both times I went out, I experienced poor weather conditions. I was delayed mostly by rain, which I had no choice but to wait out. I made sure the statue was dry before continuing my measurements. There was also a lot of light shining through the windows on 3 sides, as well as street lights and emergency lighting. In my second round of measurements, I put up a tarp to block out as much light as I could, as well as covering the sidewalk lights with a tarp as well. Finally, due to the configuration of my Raspberry Pi, I was unable to maintain a connection to UMD Wi-Fi, and I did not have access to a mobile hotspot, meaning I couldn't SSH into my Pi. So I found a single outlet in the courtyard of Van Munching and connected a 100-foot extension cable to a power strip to power my Pi as well as a monitor so I could take measurements locally. After taking measurements, I separated the Testudo from its base on all 4 sides and ran the color picker strip to find HSV values that isolated the line laser from the rest of the image. I then ran these images and corresponding HSV values through datageneration.py, which calculated distances and wrote out a text file with X, Y, and Z coordinates. Within MATLAB, I imported these text files and concatenated the base and the statue on each side. I then performed coordinate transforms, first rotating using a rotation matrix, and then translating by matching the edges of the base. There was some warping that occurred during data acquisition, so using a priori knowledge of the geometry of the base, I wrote a loop which essentially flattened out the sides. I then created threshold values based on the X, Y, and Z coordinates of the base to further filter out any residual noise. Here's the 3D point cloud of my first trial without changing any of the reflectivity of the surface or blocking out any of the light. Here's my unfiltered 3D point cloud for my second trial. Overall, the 3D point cloud was a pretty good representation of the actual statue, though there is still room for improvement. The top is not captured very well due to height constraints, and portions of the statue still do not show up. But overall, it was a big improvement over my first attempt in scanning it. I exported the combined 3D point cloud from MATLAB to a text file, which I then imported into MeshLab. I deleted any residual noise left after filtering in MATLAB by manually selecting points. I ran the point cloud through 3 iterations of Poisson disk sampling to further reduce outliers. Then I calculated the normals and performed a Poisson surface reconstruction. I cleaned up the mesh by manually selecting unwanted surface regions and deleting them. This was my final mesh. It isn't great, but you can clearly see the base and part of its shell. I'm sure that obtaining more data points would allow MeshLab to find a more realistic mesh. Overall, this course was very fun, and I learned a lot about both the advantages and challenges of LiDAR. I'm very proud of how far I've come to being able to produce a relatively realistic point cloud of a complicated geometry given the challenges I've encountered. I can't wait to see how LiDAR is further used in future technologies. Again, this is Bernard Chang, and thank you for watching my final project presentation video.